Welcome to our comprehensive guide on Rust interview questions for systems programming. Rust is a powerful programming language that has gained tremendous popularity for building high-performance, memory-safe applications. In this presentation, we'll explore the fundamental concepts that every Rust developer should master, including ownership, borrowing, memory safety, concurrency, and systems-level programming. These concepts form the backbone of most technical interviews for Rust positions. Whether you're preparing for your first Rust interview or looking to deepen your understanding of systems programming concepts, this guide will provide you with the essential knowledge and practical insights you need to succeed. Ownership is Rust's most distinctive feature and the foundation of its memory safety guarantees. Unlike languages with garbage collectors, Rust manages memory through a sophisticated ownership system that operates entirely at compile time. The concept is elegantly simple. Every value in Rust has exactly one owner at any given time. When the owner goes out of scope, the value is automatically dropped and its memory is freed. This system prevents common memory bugs like use-after-free errors and memory leaks without any runtime overhead. Ownership can be transferred between variables through a process called moving, which ensures that only one variable can access the data at a time. This compile-time approach to memory management is what makes Rust both fast and safe. Rust's ownership system follows three fundamental rules that are enforced at compile time. First, each value has exactly one owner. There can never be multiple owners of the same data simultaneously. Second, there can only be one owner at a time, meaning ownership is exclusive and cannot be shared. Third, when the owner goes out of scope, the value is automatically dropped and its memory is released. Let's examine a practical example. When we create a string and assign it to another variable, ownership moves from the first variable to the second. The original variable becomes invalid and cannot be used anymore. This prevents accidental double-free errors and ensures memory safety. The compiler catches these ownership violations at compile time, eliminating entire classes of runtime errors that plague other systems programming languages. Borrowing is Rust's mechanism for accessing data without taking ownership of it. Think of borrowing like taking a reference to a book from a library. You can read it and use it, but you don't own it permanently. In Rust, we create references using the ampersand symbol. When we borrow a value, we create a reference that points to the data without transferring ownership. This means the original owner remains valid and can continue to use the value. Borrowing is essential for writing practical programs because it allows functions to operate on data without consuming it. The beauty of Rust's borrowing system is that it provides memory safety guarantees at compile time, ensuring that references are always valid and preventing dangling pointer errors. This makes concurrent programming much safer and more predictable. Rust distinguishes between two types of references, immutable and mutable, each serving different purposes in maintaining memory safety. Immutable references, denoted by ampersand, allow you to read data but not modify it. The key advantage is that you can have multiple immutable references to the same data simultaneously, enabling safe concurrent read access. This is safe because if no one can modify the data, multiple readers cannot interfere with each other. Mutable references, denoted by ampersand mut, allow you to both read and modify the borrowed data. However, Rust enforces a crucial restriction. You can have only one mutable reference to a piece of data at a time. This prevents data races by ensuring exclusive access for writing operations. These borrowing rules eliminate entire categories of bugs that commonly occur in other systems programming languages. Memory safety is one of the most critical aspects of systems programming, and traditional languages like C and C++ are notorious for memory-related vulnerabilities. Common problems include use-after-free errors, where programs access memory that has already been freed, dangling pointers that point to invalid memory locations, memory leaks where allocated memory is never released, buffer overflows that can lead to security vulnerabilities, and data races in concurrent programs. Rust addresses all of these issues through its ownership system and compile time checks. The borrow checker analyzes your code during compilation and ensures that all memory accesses are safe. Zero-cost abstractions mean you get this safety without runtime performance penalties. The compiler catches potential issues before your program even runs, making Rust programs inherently more reliable and secure than those written in traditional systems languages. Understanding the difference between stack and heap memory is crucial for effective Rust programming. The stack is a region of memory that operates on a last-in, first-out principle, much like a stack of plates. Stack allocation is extremely fast because it simply involves moving a pointer, and all data on the stack must have a known, fixed size at compile time. Local variables and function parameters typically live on the stack. The heap, on the other hand, is used for dynamic memory allocation when the size is not known at compile time or when data needs to outlive the current scope. Heap allocation is slower because the system must find an appropriately sized block of free memory. In Rust, types like integers and fixed size arrays live on the stack, while types like string and vec that can grow dynamically store their data on the heap. Understanding this distinction helps you make informed decisions about performance and memory usage in your programs. Concurrency is where Rust truly shines, earning its reputation for fearless concurrency. Traditional concurrent programming is fraught with dangers like data races, deadlocks, and unpredictable behavior. Rust's ownership system extends naturally to concurrent programming, providing compile-time guarantees that prevent data races entirely. The language provides several built-in tools for safe concurrent programming. The standard thread module allows you to spawn operating system threads easily. Channels enable message passing between threads, following the principle of don't communicate by sharing memory, share memory by communicating. For shared state concurrency, Rust provides mutex for mutual exclusion and arc for atomic reference counting, allowing safe sharing of data between threads. The async and await keywords enable asynchronous programming for I/O-bound operations. What makes this fearless is that the compiler prevents you from making common concurrency mistakes at compile time, rather than discovering them during runtime. Thread safety and data race prevention are fundamental challenges in concurrent programming that Rust addresses through its type system. Data races occur when multiple threads access the same memory location concurrently, with at least one thread performing a write operation, and there's no synchronization mechanism in place. This leads to undefined behavior and unpredictable program execution. Traditional approaches rely on runtime checks and careful programming discipline, but Rust takes a different approach. The borrow checker analyzes your code at compile time and prevents data races from occurring. Rust uses marker traits called send and sync to define thread safety boundaries at the type level. Types that implement send can be transferred between threads safely, while types that implement sync can be referenced from multiple threads safely. The compiler uses these traits, along with the ownership rules, to ensure that your concurrent code is free from data races before it even runs. Rust excels in systems programming applications where performance, safety, and reliability are paramount. Operating systems and kernel development benefit from Rust's memory safety without garbage collection overhead. Network servers and protocol implementations leverage Rust's excellent concurrency support and zero-cost abstractions. Database engines use Rust for its predictable performance characteristics and memory safety guarantees. Blockchain and cryptocurrency projects choose Rust for its security features and performance. Game engines benefit from Rust's control over memory layout and allocation patterns. Internet of Things and embedded systems programming utilize Rust's ability to run on resource-constrained devices without a runtime. The key advantages that make Rust attractive for these applications include memory safety without garbage collection, zero-cost abstractions that don't sacrifice performance, fearless concurrency that prevents data races, predictable performance characteristics, compile time guarantees that catch bugs early, and excellent cross-platform compatibility across different operating systems and architectures. Success in Rust interviews requires both theoretical knowledge and practical experience. Focus on mastering the fundamentals of ownership, borrowing, and lifetimes, as these concepts appear in virtually every Rust interview. Practice writing code examples that demonstrate these concepts clearly, as interviewers often ask candidates to solve problems or explain code snippets. Always explain your reasoning step by step, walking through how ownership transfers or how the borrow checker would analyze a piece of code. Familiarize yourself with common Rust patterns like resource acquisition, initialization, smart pointers, and error handling with result and option types. Common pitfalls to avoid include fighting the borrow checker instead of working with the ownership system, overusing clone operations when borrowing would be more appropriate, misunderstanding when explicit lifetime annotations are necessary, and neglecting proper error handling patterns. Remember that Rust interviews often focus more on understanding the language's safety guarantees and design principles rather than just syntax memorization. Let's summarize the key concepts that form the foundation of Rust systems programming. The ownership system is Rust's unique approach to memory management that prevents memory safety issues without garbage collection overhead. Borrowing enables safe data access patterns through references while maintaining ownership rules. Memory safety is achieved through compile time checks rather than runtime overhead, making Rust both fast and secure. Fearless concurrency allows you to write multi-threaded programs with confidence, knowing that the compiler prevents data races. Zero-cost abstractions provide high-level programming constructs without sacrificing performance. To continue your Rust journey, practice ownership patterns daily through coding exercises. Build small systems programming projects to gain hands-on experience. Explore concurrent programming concepts and async programming. Study real-world Rust code bases to see these concepts in action, and master error handling patterns using result and option types. Remember, Rust's learning curve can be steep initially, but the safety and performance benefits make it worthwhile for systems programming applications. Good luck with your Rust interviews.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.